So here we have our free body diagram with all the known forces put in it. What we can see so far with this is that we don't know what the reaction vertical is at the pin, or at the roller, or horizontal at the pin. Okay? So that's the challenge now in solving this problem. How can we work this out? Now there's two formulas that we actually use. The first one is the sum of all moments equal 0, or the sum of all forces equal 0. Now you can see in this case here, we've got too many unknowns to be able to do this equation. So the equation that we were looking for is the sum of all moments. To understand what we're saying with the moments is it's literally a rotation around a point. So with the reaction right, we can't take a rotation around that because we have that ability to be have the horizontal movement. So that's going to throw things out. So what we're actually doing, we're taking the reactions around the pin. Now, in doing this symbol, like I said, it's going to be positive around the pin. So what I'm actually saying is any force that is moving this way around the pin, remember it's a rotation, is going to be positive. So RRV will be positive, whereas you're going to find these forces up here, because they're spinning in the opposite direction, will be negative. Okay, and I'll show you where that comes into play. So let's start doing this equation. I'm going to say for all movement in this direction around the pin, the sum of all moments must equal 0 for it to be in equilibrium. Okay? That means that the bridge won't fall down. It's going to actually be static. It's going to be able to sit there. No other forces in play, that's what we're going to do. Okay, so now let's start looking at this equation. So a moment, so 0 will equal force by distance. Okay, that's the calculation we need to put into play. So 0 will equal, we have, it's a positive force. Let me go back to this here. I just lost my pen. It's a positive force. A positive bracket RRV multiplied by 44 meters. Now the next force I'm coming up here to here is a negative force. So I'm going to be subtracting this. 1099 multiplied by the distance, which is 14, 18, 22, 26, 30. Next force, again, negative. Bracket 554 multiplied by 12. Next force is again negative. Bracket 314 multiplied by 4. Okay, so you can see now here, and this is what I keep saying, as long as you can see the problem, the mathematics is quite easy. It's not a difficult sum. Okay, so you can see here it's quite easy to actually start to work out. So again here I've got now RV by 44 will equal, now I've gone from a positive, so this is now a negative. Okay, so again I'm moving it across, so I need to subtract this from that side. And then I can start doing the calculations here. Clear. I have 1099 by 30. So this is 32970 minus 554 by 12 648 minus 31454. 1, 2, that's a negative number as well. I should have put that in. 1256. So here, let's just quickly add that up. 32970 minus, I didn't do it right there, minus 32970 minus 6648 minus 1256 equals negative 40874. Now, so then I've got now negative RRV equals negative 40874 divided by 44. The negatives actually cancel out, so we can get rid of that. So this will equal 40918 kilonewtons. Oh, no, that's not right. What am I doing? I'll just get rid of that because that didn't look right at all. Clear, I pushed the wrong button. 40874 divided by 44 equals 928.95. It's approximately equal to kilonewtons. Okay, so now I've started to get my calculation. So I now know that from that equation that this force over here will be 928.95 kilonewtons. There you go. Like I said, with this here, it's actually plugging in the unknowns, understanding how to use the moment force. The trick here with, though, is establishing what is going to be positive, what direction is positive, so then you can work out whether you are adding or subtracting these force by distance calculations. Once you've done that, you can establish what the reaction is at the roller.